which were the initial diodes or triodes, etc. These devices were used in the earlier part of the 20th century in electronic circuits. First, let us try to understand the term electronics. In the strict sense, the word electronics refers to the science and technology of the motion of the charges in a gas. In vacuum, the motion of charges in vacuum was studied in devices called the diodes or valves, and subsequently in the triodes, tetrodes, and pentodes. A simplest vacuum tube, called the vacuum diode, which consists of two electrodes, is basically made up of an anode, often called the plate, which is the positive electrode, and a cathode or the filament, which is the negative electrode, kept inside an evacuated glass tube. When the cathode is heated, energy supplied to it helps the conduction electrons to overcome the electrostatic attractive force of the surface of the cathode, and they are set free to leave the cathode surface. The flow of the electrons is controlled by varying the voltage between the two electrodes. Vacuum is essential in the inter-electrode space of a vacuum tube, as it helps to prevent any loss of energy that would otherwise take place if the electrons were to collide with the air molecules in their path. When the anode is kept at a positive potential, as compared to the cathode, which is at a negative potential, due to the potential difference, the electrons move from the cathode to the anode in one direction only. Vacuum tubes are also referred to as valves, as in these devices the flow of the electrons is only in one direction, that is, from cathode to anode. As such, they are useful for receiving radio signals. Some of the common types of vacuum tubes used are the vacuum diode, the triode, the tetrode, and the pentode. The vacuum diode has two electrodes, an anode, and a cathode. The triode has three electrodes, a cathode, a plate, and a control grid. The tetrode has four electrodes, a cathode, a plate, a control grid, and a screen grid. And the pentode has five electrodes, a cathode, a plate, a control grid, a screen grid, and a suppressor grid. However, in spite of their widespread use in earlier times, vacuum tubes have certain disadvantages. These are: vacuum tubes are bulky, they generally operate at high voltage around 100 volt, they consume high power, they have limited life as the cathode electron emitting materials get used up in the operation, low reliability as they are more prone to microphonics because the mechanical vibrations are transformed into an undesired electrical signal, also referred to as noise. Glass tubes are physically fragile. These disadvantages in the usage of vacuum tubes led to the search for devices and materials in which the number of charge carriers and their direction could be controlled without the added disadvantages of the vacuum tubes. The use of materials called solid-state semiconductors and devices made from them called the solid-state semiconductor electronic devices helps to overcome these drawbacks of vacuum tubes, as it was possible to control the number and the direction of the flow of charge carriers in them. In the semiconductor devices, the flow of charge carriers is within the solid itself. However, At low temperature, the charge carriers are not free to move as they do not possess sufficient energy to move. The charge carriers can be freed to become mobile charge carriers in a semiconductor by heating, applying a small voltage, or exciting through light. Use of semiconductor devices has many advantages, such as they are small in size, they operate at low voltages, they consume less power, they have long life as the solid-state material is durable, high reliability as they are less prone to microphonics. To fully understand semiconductor devices, it is important for us to understand the classification of materials on the basis of their electrical conductivity. We have learned that electrical conductivity or specific conductance is a measure of a material's ability to conduct an electric current, whereas electrical resistivity, also known as specific electrical resistance or volume resistivity, is a measure of how strongly a material opposes the flow of electric current. Solid materials are broadly classified into three categories on the basis of their electrical conductivity or resistivity. These are conductors, semiconductors, and insulators. Conductors have very low resistivity and high conductivity. Their resistivity ranges between 10 raised to the power minus 2 to 10 raised to the power minus 8 ohm meter. And in particular, metallic conductors possess conductivity in the range of 10 raised to the power 2 to 10 raised to the power 8 Simon per meter. Some examples of conductors are copper, nickel, etc. Insulators have very high resistivity and very low conductivity. Their resistivity ranges between 10 raised to the power 11 to 10 raised to the power 19 ohm meter. Their conductivity is in the range of 10 raised to the power minus 11 to 10 raised to the power minus 19 Simon per meter. Some examples of insulators are wood, rubber, etc. Semiconductors have resistivity and conductivity which lie in between that of metals and insulators. Thus, they have lesser conductivity and higher resistivity than metals, and higher conductivity and lower resistivity than insulators. Their resistivity ranges between 10 raised to the power minus 5 to 10 raised to the power 6 ohm meter. They possess conductivity in the range of 10 raised to the power 5 to 10 raised to the power minus 6 Simon per meter. Some examples of semiconductors are silicon and germanium. These semiconductor electronic devices may be made up of different types of semiconductors, such as elemental semiconductors or compound semiconductors. Elemental semiconductors are single elemental semiconductors. They belong to the fourth group of the modern periodic table of elements. Silicon and germanium are the most commonly used elemental semiconductors. Compound semiconductors are formed by using two or more elements. They are synthesized using elements from groups 2 through 6 of the periodic table. Compound semiconductors may be further divided into different types, such as inorganic compounds like cadmium sulfide, gallium arsenide, cadmium selenide, etc., and organic compounds like anthracene, doped phthalocyanine, etc., and organic polymers like polypyrrole, polyaniline, polythiophene, etc. You have learned that materials are classified as conductors, semiconductors, and insulators based on their electrical conductivity, which in turn depends on their atomic structure. For example, copper is a conductor, silicon is a semiconductor, and wood is an insulator. According to Bohr's postulates, every atom consists of electrons that revolve around the nucleus in fixed energy levels, called orbits or shells, and the angular momentum is quantized for each electron. The orbit number in which they revolve is characterized by the principal quantum number. The concept of fixed energy levels is valid only when an atom is well isolated from other atoms. This is not possible as atoms are closely packed, especially in the case of solids, and thus there are interactions between the atoms. Due to this, the outer orbits of some neighboring atoms come very close and even overlap. Hence, in the case of atoms in a solid, the electron energy is affected due to this proximity of neighboring atoms. It should be remembered that each electron still has a distinct quantum state even in such situations. This means each electron has a unique position and no two electrons see exactly the same pattern of surrounding charges. Let us consider the atoms in a solid. For example, a silicon crystal. We know that in a crystal, there is a regular arrangement of atoms with constant interplanar spacing between them. The electronic configuration of silicon is 1s2, 2s2, 2p6, 3s2, 3p2. The third orbit, with 4 electrons, is the outermost orbit. Hence, silicon has valency equal to 4. As silicon has a crystalline structure, there are interactions between the neighboring atoms. Let us assume that there are n silicon atoms in the crystal, each with 4 valence electrons. For silicon, in the outermost orbit, there are 8 energy states available, out of which 2 states belong to 3s orbital and 6 states belong to the 3p orbital. Therefore, for n atoms, the total number of energy states available in the outermost orbit is equal to 8n. At the distance between the atoms observed in crystals, such as silicon, these 8n energy states split into 2 levels, each having 4n energy states, due to the atomic interactions discussed earlier. In a crystal, each energy level or state is split up into a large number of closely spaced sublevels. A group of such sublevels with continuous energy variation is called an energy band. For a silicon atom, the lower 4n energy states contain electrons that are in bonding, and such energy states are called the valence band. Therefore, the term valence band refers to a group of energy levels which contains bonded electrons. We know that the electrical conduction in solids takes place by virtue of electrons, which are free to move, that is, by means of free electrons. Since the electrons in the valence band are bonded, they do not contribute to the electrical conductivity of a material. The higher 4n energy states contains those electrons which are free to move about, and as such, they contribute to the electrical conductivity of the semiconducting material. The group of energy levels occupied by such electrons that helps in conduction is called the conduction band. Let EC denote the lowest energy level of the conduction band. let EV denote the highest energy level of the valence band. The difference between EC and the EV is the energy band gap or energy gap denoted as EG. The valence band electrons can move into the conduction band by gaining energy equal to the energy band gap EG. Thus, there exists a band gap between the lower valence band energy levels and higher conduction band energy levels. For a silicon atom, this energy gap Eg is about 1.1 electron volt. This means that for a valence band electron to move in the conduction band, it needs a minimum energy of 1.1 electron volt. At room temperature, we find that a few electrons of the valence band gain thermal energy equal to the energy band gap to move into the conduction band, and hence become free electrons. The vacant energy levels in the valence band create the opportunity of other valence band electrons to move into them. Therefore, in such solids, conduction is possible due to the conduction band electrons, as well as due to the vacancies in the valence band. This is the reason why a semiconductor displays higher conductivity at higher temperatures. However, as the temperature decreases, we find that there are fewer electrons in the conduction band than at higher temperatures, and hence conductivity decreases. At the temperature of 0 Kelvin, the conduction band is practically devoid of any electrons, and as such, there cannot be conduction possible through the semiconductor. Hence, at 0 Kelvin, a semiconductor behaves as an insulator. This is the case of the semiconductor crystal. It is important to note that the band gap is different for different solids. Let us now look at the specific case of solids where the energy band gap Eg between the conduction band and valence band is very small, or the conduction band overlaps the valence band. When such an overlap occurs, the band gap Eg is nearly zero. In solids where a very small band gap exists, with no external energy available, there are no electrons in the conduction band. When a small energy is supplied, the valence band electrons move into the conduction band. Now let us look at the situation where the conduction band overlaps with the valence band. In this case, the valence band electrons are available to move into the conduction band and thus are readily available for conduction, which happens in the case of metals. Since a large number of electrons are available for conduction, the electrical conductivity is very high for such solids. We know that solids having very high electrical conductivity are called conductors. For some solid, there exists a very large energy band gap greater than 3 electron volt. In such solids, it is practically impossible for the valence band electrons to move into the conduction band, since the energy required is very high as the band gap is very large. Such materials then have very few conduction electrons, and hence have very low electrical conductivity. Such materials are characterized as insulators. In semiconductors, we have seen that a finite but a small band gap of less than 3 electron volt exists, and as such, by supplying sufficient energy, the valence band electrons can move into the conduction band. Therefore, the semiconductors have conductivities between that of the conductors and insulators. Thus, we see that on the basis of energy bands, materials can be classified as conductors, semiconductors, and insulators. With conductors having a very small or nearly zero band gap, semiconductors having a finite and small band gap of less than 3 electron volt, and insulators having a band gap of greater than 3 electron volt. A semiconductor without any artificially added impurity is called an intrinsic semiconductor. Both silicon and germanium, the two most commonly used semiconductors, exist as intrinsic semiconductors. Let us take a look at the atomic structure of silicon and germanium. Both silicon and germanium have 4 valence electrons. In crystalline form, each silicon and germanium atom uses its valence electrons to form 4 covalent bonds with 4 surrounding atoms. Let us use the crystal structure of silicon to further study intrinsic semiconductors. Remember, the following discussion applies equally to germanium in its intrinsic form. At absolute zero, all the covalent bonds in the crystal lattice of an intrinsic semiconductor are intact. Thus, at absolute zero, there are no free electrons to occupy the conduction band, and the intrinsic semiconductor behaves like an insulator. However, at higher temperatures, some electrons gain enough thermal energy to break free of the covalent bonds in the crystal lattice. These free electrons move to the conduction band, and the material starts behaving like a semiconductor. Note that each electron that moves to the conduction band leaves behind a vacancy in the valence band. This can be visualized as breaking of a covalent bond, where an electron becomes free and leaves behind a vacancy in the covalent bond. An electron breaking away from a covalent bond takes away a unit negative charge with it, leaving behind a vacancy with an assumed unit positive charge. A vacancy with a unit positive charge in a covalent bond between atoms of a semiconductor is called a hole. Thus, whenever a covalent bond is broken in an intrinsic semiconductor, a free electron and a hole is created. We refer to this as an electron-hole pair. Hence, in an intrinsic semiconductor, the number of free electrons is always equal to the number of holes at any given moment. Consider a hole or a vacancy at position 1 in the crystal lattice of a semiconductor. Now, an electron from position 2 can jump to occupy the vacancy at position 1. This fills the vacancy at position 1 but creates a vacancy or a hole at position 2. Similarly, an electron from position 3 can jump to occupy the vacancy at position 2. This fills the vacancy at position 2 but creates a vacancy or a hole at position 3. As a result of such jumps of electrons across covalent bonds, the holes or vacancies appear to move across the crystal lattice of a semiconductor. Note that the movement of holes occurs because of the movement of electrons across covalent bonds in a semiconductor, and not because of the movement of free electrons. Thus, there are two types of moving charge carriers in the crystal lattice of a semiconductor: the negatively charged free electrons and the positively charged holes. When an electric field is applied across a semiconductor by connecting it across the terminals of a battery, the free electrons move towards the end connected to the positive terminal and generate an electron current denoted by IE. The holes shift towards the end connected to the negative terminal and generate a hole current denoted by IH. The total current flowing through the semiconductor is equal to the sum of the electron current and the hole current. If a free electron collides with a hole, it fills the vacancy in the covalent bond without the generation of any other hole. This is called the process of recombination. Under thermal equilibrium, the rate of generation of free electrons and holes in a semiconductor is equal to the rate of their recombination, so that the density of charge carriers in a semiconductor remains constant. As we learnt earlier, a pure semiconductor without any impurities in it is called an intrinsic semiconductor. Both silicon and germanium exist as intrinsic semiconductors. There are two types of charge carriers in the crystal lattice of an intrinsic semiconductor: the negatively charged free electrons and the positively charged holes. The conductivity of an intrinsic semiconductor increases with rise in temperature, as more number of electrons break away from the covalent bonds of the semiconductor atoms. However, at room temperature, intrinsic semiconductors have very low electrical conductivity. The electrical conductivity of an intrinsic semiconductor can be improved by increasing the number of free electrons or holes in it at room temperature. When a small amount of suitable impurity, say a few parts per million, is added to an intrinsic semiconductor, its conductivity increases to a large extent. A semiconductor that has an added impurity to increase its electrical conductivity is called an extrinsic semiconductor. The process of adding the suitable impurity to a semiconductor is called doping. Thus, an extrinsic semiconductor is also called a doped semiconductor. The impurity atom added to a semiconductor to increase its electrical conductivity is called a dopant. During the process of doping, the dopant gets positioned in the crystal lattice of the semiconductor. It is important that a dopant does not distort the crystal lattice of a semiconductor. For this, the dopant atoms of the semiconductor crystal should be comparable to the semiconductor atoms in size. We have learned that both silicon and germanium are tetravalent. That is, each of their atoms has 4 valence electrons. Commonly used dopants are either trivalent or pentavalent neighbors of silicon and germanium in the periodic table. Commonly used trivalent dopants that have 3 valence electrons are boron, aluminium, and indium. Commonly used pentavalent dopants that have 5 valence electrons are phosphorus, arsenic, and antimony. The addition of trivalent and pentavalent dopants